natives in Berlin. So Darwin Recruitment will not only provide you with the tickets, but also pay for your flights and also your accommodation in Berlin as well. So it's an excellent prize to win tickets to one of the top data conferences in the world. To find out more information about how you can win that competition, in the blue pads that we've provided, there's some information in there. That's a small gift from us, so please feel free to take those when you leave. Before kicking on with the evening and the event, I'd like to first of all introduce myself to you, to introduce Darwin, tell you a bit about what we do and why we're hosting this world tour. So I'm Daniel Butler. I'm our data science specialist for our Swiss team. I've been at Darwin now for about 6.5 years. Throughout that time, I've predominantly only worked the Swiss market, so I'm very familiar with being here in Zurich. At Darwin, we've been working the Swiss market now for 17 years. We have a Swiss license, but we actually officially set up our Swiss business in Zurich in 2012. We're an award-winning business. Last year at the Recruitment Awards, we were shortlisted for the best international business and also the best technical recruitment company as well. Within Darwin, we are a leading supplier of both digital and data talent across Europe and the US. And within Darwin, we have specific teams that focus on specific countries. Within those countries, we work a range of customers. So these customers include startups all the way through to multinational corporations as well. Within the Swiss team, we have 11 specialists and consultants who focus on niche technical specialisms. And within the Swiss team, we have a dedicated data team, and the three of us are here today. So myself, I focus on data science. We've got Luke. Please put your hand up, Luke. Luke focuses on data engineering, and Jacob alongside Luke there. Jacob works with professionals working in both data engineering and data science as well. Combined with the three of us, we have over 12 years industry experience. During the time of working the data market within Switzerland, we've noticed a common theme. That common theme is that requirements within data science quite often look for people who have a specific educational background, who have technical knowledge, but quite often they also look for people who have very specific, relevant industry experience. And here's the problem that we face and the difficulty we find is that certain kind of specific professionals are only sometimes interested or relevant for specific roles within data science. As a result of this, as specialists, I think it's vital for us to really understand customers, what they do, but also understand candidates, what you're interested in, what you really do, so we know exactly what to look out for you and what interests you. Events like this obviously really help. We get to learn a lot. Data science is not what we do, so it's good for us to learn. And then also as well, an added advantage is that we're connecting the community as well and getting to know you guys, and you can all get to know each other. Last week I was actually looking online and I read that in the US they predict that by 2020 there's going to be 180,000 vacant positions within data science. Now that far greatly outweighs the number of professionals working within data science currently. So I think it's clear to see that it's a great time for data science. And because of that, it's vital that we really kind of keep up to date with current trends and provide candidates and customers alike with that information and that feedback. I'd now like to move on to our speakers this evening. So our second speaker is Marco Andrea Buchmann. Marco Andrea is head of AI at MaCX Asset Management. Marco was actually a candidate of mine. We used to speak quite regularly on almost like a weekly basis. Marco, since joining MaCX Asset Management, has stayed in touch with me, and he's going to speak to us today about neural networks and how it's going to have an impact on the finance industry. Our first speaker is Lisa Falco. Lisa is Director of Data Science at Ava Women. Ava is an award-winning startup who kind of use machine learning to help predict women's fertility and therefore enhance the chances of starting a family. For someone like me, I have 2 young children. I really think it's a great way of using technology and a really interesting business. Before we welcome Lisa to the stage, I just want to add one thing. This event is being live streamed and recorded as a result of that as well. But all of our other events throughout the Data World Tour are going to be live streamed as well. So please look out on LinkedIn for more information on that so you can follow those. And Marco Andrea's slides are also going to be available on SlideShare as well. Okay, thank you very much for listening, and I'd like to welcome Lisa. Thank you.
Thank you all for being here and listening to me talking about fertility. I've been in contact with Darwin because they also wanted to sell some of their candidates to us. And we found it really a hard struggle also to find good data scientists. We find many good and smart people we're in contact with every day. But as unfortunately, we often look for very specific qualities and a lot of experience, which is sometimes a bit challenging to find, but yeah, maybe I'll find it here tonight. So before I start, maybe just wanted to be a short introduction to myself. So my name is Lisa Falco, and I come from Sweden. Where I did my first studies, and then I have a PhD from Lausanne in Switzerland, EPFL. After that, I joined a startup here in Zurich, where I worked with physiological monitoring. We were trying to track glucose changes non-invasively, also through sensors on the skin, and that was really exciting work. And we went bankrupt after 5 years, and we all got fired. So the startup world can also be like that. It's a bit different from the startup world I'm in right now, but who knows? We're only 4 years old. So after that, I was working as a product manager for a few years when the founders of Ava approached me and asked me to join them, basically for what I've done with the other startup. And I joined Ava in 2015 as director of data science. So I'm very excited to be there, and it looks better this time because yesterday we won for the second year in a row the award of Best Startup of Switzerland. So, what I want to talk to you about, with you about today, is a little bit the vision of Ava, what we do, and why do we think we can use wearables and so why do we think we can use wearables and AI to provide good fertility predictions. And also I want to tell you a little bit of how our algorithms has developed over time, what different steps we have gone through as our amount of data has evolved, and a little bit about the challenges we see in the future. So women face various challenges throughout their reproductive age. It begins when you get your first periods around already 11, 12 years old, just to understand your body, how it works, why do I get my period, what's really happening to me. And then for many years, in our early years, we spend a lot of effort trying very hard not to get pregnant. And after we've been spending maybe 15, 20 years hard not to get pregnant, then suddenly we want to become pregnant, right? And this is where it can become tricky sometimes. Up to a third of all couples actually experience some difficulty in getting pregnant. It can be everything from it just takes a bit longer than what you had expected to actually have fertility issues, both on the side of the man and on the woman, of course. Then once you get pregnant, you get very nervous in this stage. There's so many things that can go wrong, which you become painfully aware of. And about 10% of all pregnancies have some of issues. It can be premature birth, you can have problems with your placenta, and in the worst case, even preeclampsia. And then, of course, after the pregnancy, and you've gone through this cycle, pregnancy, contraception, trying to conceive, pregnancy, this is a whole cycle. You, in the end, will reach menopause, where your cycles will end. So our vision in AVA is to accompany women throughout this whole reproductive age and provide the women with the help she needs to better understand her body and to help to prevent a few of those issues that can happen. Now this didn't work. Okay. So what is the solution that we are providing? Well, our system is composed of three components. So it's a bracelet that you see on the bottom. The bracelet is worn at night only and only collects data when you're sleeping. Then in the morning, the bracelet is synced with the app, and all the data is sent to the cloud, where our algorithms are working. The data is being processed, and all the output on the fertility is then being sent back to the app for a comprehensive view for the user. And the bracelet itself collects 9 different physiological parameters. It's breathing rate, skin temperature, heat loss, pulse rate, heart rate variability, movement, bioimpedance, sleep, and perfusion, blood perfusion, that is. And with our solution, now we had a lot of success lately. So we launched our first product in July 2016. And you can see how our sales numbers has increased until this ends in March 2018, but it has continued to increase even further. So at the moment we have, I don't know, we have maybe 50,000 customers at the moment using AVA, and we have daily pregnancies coming in. I think we have about 300 pregnancies a week of our users, so we have a lot to celebrate, and we get to look at a lot of cute baby photos as well. So now we have our baby number 1,000 that was just born. So why does this work? Why can we use such a fertility? Do I need this microphone? Yeah, maybe. Do you hear me in the back if I don't use microphone? No? Okay, sorry. Okay, I need the microphone. Sorry. I was trying to get avoid it. I don't like it. So here you see a menstrual cycle. And a lot of things is happening in the background in the menstrual cycle. The first day of the cycle starts with your first day of your menses. And it lasts until the day before the next menses. So of course these borders of the menstrual cycle are very easy to recognize. That's not an issue. What is an issue, and it's difficult to recognize, is this day somewhere in the middle, which is the day of ovulation. And the day of ovulation is then preceded by 5 days of fertile days. And together with ovulation, that gives a sum of 6 fertile days in your whole cycle. And it's only during these 6 fertile days that you can actually become pregnant. And these are very difficult to recognize if you don't know what to look for and if you don't use AVA, of course. So we have different hormones that change throughout the menstrual cycles. And the ones that we are the most interested in AVA is estradiol. This is an estrogen. This is a purple line. This is peaking during the fertile phase. What this does is that it creates a really nice environment for the sperm inside the vagina so they can live long. Because you only get pregnant if the sperms are already there when the egg is being released on the day of ovulation. Afterwards, once the egg has been released, you have a rise in progesterone. The role of progesterone is to improve the wall of the uterus so that the egg can implant there. And why are these hormones important for AVA? It is because they are actually driving our signals. So yeah, maybe I should just mention like the average cycle length here is 28 days, and the average luteal length is 13 days. So, but as you all know, averages is very nice in average, but it doesn't apply to an individual. So you don't know how long this phase is for one person, even though you would know the length of your cycle. And AVA are measuring signals that actually correlates to estradiol and progesterone. So what estradiol does is that it pushes down the temperature, so it becomes at its lowest just in the fertile phase, but it drives up heart rate. So heart rate starts to increase actually just before the ovulation. And then progesterone kicks in. And progesterone is a very strong driver of both of heart rate, breathing rate, and temperature. So this makes it then more possible to pinpoint the day of ovulation. So what we are having is actually 5 different algorithms that are operating in different phases of the menstrual cycle. So we have one algorithm. This star represents approximately where this algorithm is acting. So in the beginning of the menstrual cycle, we have one algorithm trying to predict where the fertile window is going to be. And this is mainly based on priors. So statistics about menstrual cycles in general, and then specifically for this woman that we've gotten to know after a while. The second algorithm is kicking in later during the menstrual cycle, where we're actually detecting the entry of the fertile window. We're detecting the temperature going down and the heart rate going up. So here we use a combination of both priors and signal, because this is physiology. We can't do it with only the signals because they are quite noisy, but in combination with priors, we manage to pinpoint it really well. And then we use another algorithm to detect the kick-in of the progesterone, and then hence the exit of the fertile window. And then we have another algorithm after you've ovulated here to make sure that to see if the signals are indicating that the progesterone were really rising as we would have expected. Because sometimes it's happened that the ovulation doesn't take place even though you have the indication that it would. And then the progesterone doesn't rise. And if the progesterone doesn't rise, then the temperature and the heart rate will not rise either. So we have another algorithm based only on the signals to check that the ovulation took place. And at the end of the cycle, we look back on the cycle and run another algorithm because, of course, when you do it looking back offline, it's much easier to get the precise pinpointing of the ovulation itself. And there we use this information to feed in the priors for the next cycle. So like this, we become better and better for every cycle. And what does our data look like then? Actually, our first issue is that we have a lot of data with very few references. Like when you want to build an algorithm, this can be really tricky. So our data looks like this. For one night, this represents one night, we measure approximately 8 hours of data. This is sleep, this is bioimpedance, this is temperature. Yeah, it's even hard for me to recognize all these things. It's heart rate variability. So we have a lot of information. However, what's tricky in the beginning is that we only have one reference point when we want to build our algorithms. All our algorithms are built from clinical data, a clinical trial. And you can get the day of ovulation with a hormonal test. So for all this data for every night, we just have one reference point to train our algorithms on. So what we did first to make a shortcut was to find representative features to simplify our data set. So we would get just one data point per night per signal. So here's 2 of the signals that are maybe the most significant. You have the temperature going down here, reaching its minimum just around ovulation, and then rising up again. And then you have heart rate starting to rise before ovulation, and then goes up and peaks, really showing a nice progesterone curve. So these data are amazing to work with when they look like this. Most of all, they look like this, of course. So this is why we start needing more things. If all of it would have looked like that, we wouldn't need machine learning. We could just have done it, I don't know, just simple thresholding, and we would be done, right? So a little bit on how we then have developed our data. As I mentioned in the beginning, we had a clinical trial with a few cycles in it. So when we launched our device, we had approximately 100 cycles to work with. You can't really do much machine learning or advanced algorithm in that stage with 100 data points, right? So we used a lot of literature, try to really understand how the woman works, what we could expect from the signals, and then we were building a model, an expert model, us thinking and rubbing our foreheads, trying to figure out what the algorithm should be like. So this is why we started. So this is what we based our algorithms on, and then we would feed in the signal and the women-specific info to then get information on the app. This is what we started with before the launch. But of course, then once we launched, new data came in every day. So both we scaled up our clinical study to include much more women. And of course, we had all the user data coming in. So this made it possible for us to start working with machine learning and more advanced algorithms. And in our clinical data, we quickly got up to about 1,000 menstrual cycles, which is when we could start doing machine learning. So our first approach was first to go through, you have all your raw data here. Then we kept doing the simplification of the signal features. And then we spent quite a lot of effort trying to do these engineered features to really model a shift. Are we observing a shift in the signals? What kind of changes are we expecting to help the algorithm, give it a little push to become better? And the first classifier we started, I don't know, do you see this slide? Was a random forest classifier. Then after a while, we figured out, started getting really a lot of data from our users as well. And we found out a way that we could actually reference, based on the clinical data, we could develop a really good offline algorithm. Offline, as I mentioned before, is when you look back on the menstrual cycle in the end and then pinpoint the day of ovulation. And we managed to develop a really good algorithm for this. And then we could use this to start labeling our production data. And now we start talking about real amounts of data, which is very exciting. So as of 10,000 good cycles with good things, we started doing our first deep learning algorithms and our first neural networks. And now I think we have about 100,000 cycles, of which we can use, I wouldn't even say that we can use half, but at least we start getting a rather significant data set. And of course, the idea with this is that we could then stop slowly our engineered feature step to make the algorithms learn more by themselves, would allow them to capture more variations that we haven't thought of. This is, of course, in theory, and in practice, this engineered feature still has a very strong value, so we do keep them in, but we also feed in the raw signals because there are so many variations there that we, as humans or as limited data scientists, we don't see. So this is really what our neural network is helping us with. And what we do to build our neural network is we are using convolutional neural networks. And so these are specialized, you probably all know, is specialized in image recognition. So what we do is that we create an image out of our signals. So we map it. So our signals is then a one-dimensional, just like one line here represents one signal over time. And then we have all these different signals. So we just add them, which creates an image of our data, which makes it possible to use convolutional neural networks. Yeah, there are many reasons, as I already mentioned. I mean, we really do get a much better performance by using neural networks. And it's easier for us to include information from many sources because we don't need to analyze them beforehand. We don't need to build these engineered features, which allows us to progress faster. And we can, capture more variation. And what's really interesting is the more data we collect, the better we become. So where do we see the future? So what we want to do next, our next step, is to go even deeper, build even deeper networks, and then skip this step as well and start training directly on the nightly data, because we lose, of course, a huge amount of information when we go from the raw data to the signal features. And by letting our network see the whole picture, we hope that we can really make a lot of progression. This is our next plan. And other challenges, I mean, we face a lot of challenges with our data, but I'm not allowed to talk about them. But some issues that we also have when we work with a customer product, which is quite interesting to always bear in mind. I think it's also, as a data scientist, you have to think of all aspects of your problem, not just the data itself or the algorithm itself. It's that there are actually users using this device, and their behavior has a very strong influence on our product. And in the beginning, women would put on our bracelet, wear it one night, and then when we look at it, it's like, why don't you tell me when I'm fertile? It doesn't work. You don't put it on and you don't see anything. So you need to work a lot with the comprehensible UX, teach the customer how to use the device properly, and that it's important to use it over the whole menstrual cycle, because of course also many women, they would stop once they have their ovulation, because when you once you have ovulated, you have no interest anymore. But if you don't keep using it the whole menstrual cycle, we can't learn and we can't become better for your coming cycles. So we are working very closely with our product team to make sure that we teach the users to do this the best possible way. And of course, there can be many reasons that data are missing. They forget to put it on, they forgot to charge it, and the battery dies after 1 hour. And we require at least 3 hours of sleep to even give them any input. So there are many issues related to that. And in general, in digital health, like one thing we are thinking a lot about, and that we also think we address the right way, is with wearables and AI and all this. We want to be more than a hype. We just don't want to be like, now Fitbit has survived a long time, but the average user uses this for 3 months. We want people to really keep on using it and stay in it for a long time. And what are the things we are thinking about the most there is, we do think we solve a real problem. And I think this is very important for any product that you develop. You have to bring a real value to the customer and something that's used in your daily life. And especially, we are very close to the medical domain, and we are even going medical because we're going into contraception as well. So it's super important that what we do is based on solid science. So we spend a lot of time doing clinical study, validating our algorithms. It's also quite, it will be quite tough. FDA is looking very much into right now how are they going to regulate self-learning algorithms and all these AI things that are coming into digital health. And it's very important that we are being proactive there, that we spend this money and energy to validate what we do, that we can really trust it. I mean, for fertility, worst case, you don't get pregnant, but contraception, you don't want a flood of women being pregnant. Who doesn't want to get pregnant? That's not a very positive thing. But we really believe we're doing this. So I believe it's looking well. So thank you very much for your attention. And here on these pictures, you have our data science team to the left. We are actually, at the moment, mainly women, and David. But I just hired 3 more men because I thought that we needed some more diversity in the team. And so I quoted in a few men. They are also very competent. So, but they're also allowed to work with us. And here to the right, you have Jace. This is our first Ava baby who was born. So the one who was conceived thanks to Ava. Yeah, thank you. I think we have time for questions. Yes, sir. I think I can hear it, but...
I read that you're working on an algorithm for women with irregular cycles.
Yes.
Like, that's a whole different challenge. So if you have something to say about it that you can share with us, how you tackle that problem.
Absolutely. What's really challenging with women with irregular cycles is that we can't use the priors. So it was really, in our first algorithm that we launched it with, it would have been almost impossible to do this because the prior was so important. But so what we do basically to train now is we just cut time, the cycle day, completely out of the equation and only look at the signals. So the performance for the irregular cycles will be lower than it is for the regular ones because you can't weigh it in. But for irregular cycles, the women don't really have a solution. So even though we would be not as good as the regular ones, it would still be a good choice for women. And we are getting our first results on this, and we also do it with CNNs. So hopefully I'm not allowed to give any time plans, but hopefully it will be there. Any other questions?
Also, for your normal customers, how many cycles do you recommend they should go through before your accuracy is good enough? Or is it right out of the box?
In our earlier algorithm, normally a customer would become satisfied after 3 cycles. Then we'll get happy. But with our newer algorithms, where we weigh in the signals much more, actually we haven't got any data, but we really, the more signal-driven we become, the faster it would go. And for irregular cycles, you kind of have to be good at the first one because every cycle will be like the first cycle because you don't have any priors. So, so hopefully now already we're better faster, but eventually it should be up the first cycle. But it's not yet the case, unfortunately. Other questions? Yeah, there's one more. Yes. Yes.
But what is the incentive to continue using EVA during pregnancy, for example? Is there some of the pregnancy issues could be somehow reflected in the signal and detected such that the woman would be more incentivized to wear it throughout the pregnancy?
Yes. Something that's very dangerous when you're pregnant, I mean, this is, what would be the incentive for women to use EVA during pregnancy? Which is a very good question, because when you only look at the signals, right now they're not very incentivized to use it. But something you want to avoid at all price when you're pregnant is infections. And then, right now we're not providing this as a service, but eventually all our signals would react really strongly as soon as you get an infection. And we are doing our first clinical trials on this to be able to detect infections. And of course, what we really want to be able to do is preeclampsia. I mean, the day we can say that we can detect preeclampsia really early, this will be a gold mine. And we're starting the clinical trials on this as well. But this is, I mean, this is really a medical device then, so it needs to be very solid. So we can't go there all. In the very beginning of EVA, we went like the tech way, just launch an MVP, just make sure you get it out there as fast as possible. Our CEO was saying, like, if you're not, in Silicon Valley, they say if you're not ashamed of your first product, you're too late. And we were a little bit on this, really pushing it out. And now we've been working on the quality, and now we have really reached a state where we're proud of our product, and you know, now I can recommend my friends to wear it. But when we go for pregnancy and contraception, we can't do it the tech way. We need to do it the medical way. So it changes a lot. Yeah. Okay, and one more, yeah.
Yeah. To make it contraceptive method. Isn't it the other group?
Yes.
Women?
That is very true. So the question was if we will have a lot of test women, especially when we develop contraception, because our current user group are TTC, that means trying to conceive customers, and of course our contraception customers will be very different, and this will be very challenging. So right now we are developing the algorithm on our TTC community, but we cannot launch the product before we have gone through a clinical trial that is showing something it's called a Pearl Index. And the Pearl Index is how many pregnancies you expect in 100 women years. So you need 100 women for 1 year, but of course we'll have a much larger trial to make and this will be on like normal women. And there are of course many challenges. TTC, when women want to become pregnant, they party less, they have more regular lifestyle than maybe the average 25-year-old. Yeah. Yep. Okay, thank you.
So my name is Andrea. I work at MaCX. We're a quantitative investment firm. So basically, we invest money for our clients using algorithms. So not portfolio managers saying, you know, this case is similar to, I know, Japan in 1996, so we need to do this, but rather having algos invest for us. I actually studied particle physics, so something slightly different to what I'm doing right now in a sense. I did my PhD at CERN. After CERN, I joined AHL, which is part of Man Investments, so the biggest publicly traded hedge fund in the world. And then I left a couple of years later, and now I work at MaCX, which is very similar, just way smaller. Anyway, so today I'm here to talk about neural networks in finance and give you a couple of examples. So, so before jumping right into the main topic tonight, I'm going to give you a very quick overview of what parts there are in finance. So because there's basically two sides. There's the sell side, which is investment banks, etc. Those are the guys that are selling research, selling securities, advice, and so on that they create to investors. So investors like you and me, but also to companies. The people here really have, well, usually have data science background, so mathematicians, sorry, let me get out of the way. Mathematicians, physicists, and so on. There's a lot of them there. A lot of them are engaged in option pricing, those kinds of things. And then there's the second side, which is where I'm at, the buy side. So here we have hedge funds, mutual funds, pension funds, and so on. We are the guys actually buying the securities, and our goal is to make investments that align with our investors' expectations. Right, so here again, you will find a lot of people with data science backgrounds, which is, well, the same guys as before. And what we do is we basically do data analysis in order to spot patterns, for instance, using neural networks. All right, so just to get it out of the way, sell side first. So on the sell side, we have banks, as I mentioned before, and those guys actually started very, very early with evaluating AI in general and also neural networks. And some have already actually managed to implement those solutions and have them in production. And so some examples that I've found are here. So the first one that really surprised me was the analysis of legal documents. So JP Morgan, actually, they have a very, very nice machine learning and AI pipeline that analyzes contracts. And yeah, it's super fast. So I managed to review a whole bunch of legal documents in 3 seconds that would have taken lawyers 360,000 hours. So that's quite a bit more efficient than lawyers. Yeah, also nice cost savings. But anyway, the second example is customer interaction. And this is a really big topic apparently now. So customers apparently frequently ask very similar questions, such as, you know, what's my current balance in my bank account and things like that. They're really trivial to do. By the way, the slides are also online afterwards. Right, so places that are now introducing chatbots are, for instance, Wells Fargo, HSBC, Bank of America, and also UBS. The one from HSBC I've actually used. It might not be the best, or I hope it's not a good example of the whole thing. So there's lots of room for improvement there. I cannot speak about the other ones. Right, so some further examples include fraud and money laundering detection. So they're basically looking for fraudulent activities. And of course, money laundering. This is, for instance, used at Credit Suisse, which is an example that I've heard quite a bit about. Citigroup is also doing this. There's many, many more, but I don't really want to go into every single one of them. In general, they're in the process optimization kind of category. Then JP Morgan is also trying to detect failed trades. I think it was Wells Fargo, ironically, that validates account closures, but clearly not credit card issuance. Sorry, forget that. OK, so this is basically the very, very brief overview of, of the sell side. So now let's go to the buy side, so hedge funds and so on. What do we do? So as I mentioned earlier on, and I'm still in the way, as I mentioned earlier on, we're basically trying to make investments that align with what our investors expect. So there are two different approaches, and then I'll get into the more interesting part. One is that you have an investment manager that has a lot of personal experience. So they will tell you about, you know, how oil is going to move in the next couple of months based on an in-depth analysis of, I don't know, Saudi Arabia or whatever. And then you have the second group that includes myself, where we use statistical techniques and lots of data in order to see whether there are any patterns that have some predictive power. And so based on that, we're able to, you know, predict to some degree what's going to happen with securities. All right, so let's look at this one because it clearly matches the whole theme a lot better. So what we try to do, as I mentioned, is we try to predict how markets are going to behave on very different timescales. So there's people looking at, you know, how shares are going to behave over the next second or even millisecond. And then there's others that think more in terms of weeks or months or even years. So there's very different time scales. And we can use behavioral patterns. So we get some input from psychology. And we can also use many more interesting approaches, such as neural networks that I'll get to in a minute. So just to give you an example of what such a strategy can look like, I thought I'd start with something very simple. So it's known that information gets distributed not in a kind of explosive way. So it's not like there's one bit of information everybody's informed, but rather it kind of is distributed slowly. So if some share is starting to increase or to tank, not everybody's aware of it. But at some point they see the chart and they think, oh crap, I've been missing out, and so I need to invest. And then there's more and more people coming on board. So right, information spreads slowly, more and more people start to follow. By the way, also always include sources. So if you look at the slides afterwards, you can get some more information there as well. Now, based on this very simple pattern, so people catching on to information, we can create a strategy. It's been around for a really long time. It's called trend following. Basically, you look at what has been going up, and you buy into that. And you can realize that with moving averages, for instance. So I have a slow moving one and fast moving one. There's a nice example at the second link here as well. And yeah, this actually works. And there's many, many funds that do this and do that quite successfully. And that's not the topic today. Anyway, so in general, we try to spot patterns, make predictions, and now we get to the real main part of the presentation, which is how we can actually use AI for this. So I think the spotting pattern part already kind of rings a bell. But there's more that we can do, because we can also process data that we would not be able to use without AI. So for instance, it's very hard to imagine doing linear regression on some text or some images or something like that. There you just have to use AI. Those are also some of the examples that I'll bring, or that I'll go into in a second. Right, and then another interesting part, another example here, by the way, is we're able to combine information in a more meaningful way, in a nonlinear way. Right, and so now to the examples that I've promised now like 3 times. First up, oil price. So this is quite an interesting one, because I was completely stunned when I first heard about it. The method is you can actually use satellite imagery, as you see here on the right, and then you can detect shadows. So the thing is, in Texas, no, not true, in Oklahoma, there are these huge storage tanks, as you can see here, as seen from a satellite. And they have a floating top. So depending on where the top is, they cast a shadow. So you can see the shadow here, also marked in red. And so if they're full, then the shadow is bigger. If it's empty, the shadow is way smaller. So based on the shadows that you can recognize using convolutional neural networks, you can infer the storage level. And based on the storage level, you kind of know whether there's a lot of supply or not. And particularly, you can compare it to yesterday or the week before, and you know whether there's more supply now than before. And so based on the storage level, you can, well, more or less, you can take a guess at how the oil price will actually move once people catch on to that. So you have some kind of edge, right? OK, so that's the one that I thought was really awesome. And this one is even more awesome, because you can go take this a little further. So this is crop yields. So basically, you try to predict how the next harvest is going to be. So how do you do this? You, again, use satellite images. You combine that with weather data. You can actually see how the soil is doing with different wavelengths. And you combine all of that. And with that, you can get some prediction for the crop yield this year. And if you know that the harvest is going to be really bad, you kind of know that prices are somewhat likely to move up. And if you know that the harvest is going to be really good, well, then the opposite is going to happen. So you actually know this based on satellite imagery, and you don't need to send anybody into, I don't know, Idaho or wherever to really see how corn is growing or whatever. So you can see it using a satellite, right? And then the last one, which is kind of a creepy one, right, you can also predict sales by counting cars. So again, I know it's again satellite imagery, but it's so nice to illustrate. So what you can do is you can use a database of store locations, and then basically look at the satellite images, and then you can see all the cars that are parked there. And so the hypothesis that more cars equals more sales is probably not one that a lot of people would challenge. So you can, for instance, compare the number of cars that are parked in front of Walmart this year and compare it to last year, and therefore infer whether, well, maybe sales are going to move up, right? Of course, not like all the other ones, this one is not perfect because, for instance, you know, if Walmart is super popular, maybe some people will park their cars at Sears. That does not mean that Sears is back. It just means that, you know, the parking lot is too small. But still, this is a very nice way to actually know something about sales and predict them, and therefore the ahead return. Right, so I've shown satellite imagery so far. As I said, it's really nice to actually show this, and it's very, very comprehensible. It's not limited to satellite imagery at all. So, for instance, you can also use NLP to explore some additional resources, for instance, news or Twitter, not just the one guy, but many, many other people, and get a very nice picture of what's going on. Right, and so I wanted to show you with one example how this can actually work. Not the NLP part, but a strategy in particular. Right, so there's this very nice paper that I've also included in the references. It's from 2003, so it's been quite a while, but they actually managed to show that neural networks really add quite a lot of value 15 years ago, and now you can imagine what happens today. I mean, the field has changed dramatically. Right, so they use 3 different approaches. They use very standard OLS, so very simple regression. They use logistic regression, and they use neural networks. They have 18 years of data. They have 60 different features, and they try to predict a 1-year ahead return. So where are the shares going to be 1 year from today? Which ones are going to be the winners? Which ones are going to be the losers? Right, and so they use a classification approach. So basically, they look at what is the median return, and the ones that are below that are the losers. The ones above that are the winners. So yeah, category 1 underperformers, category 2 overperformers. So that's slightly more formal for winners and losers. And there's also a regression way of doing this. Right, so that's the basic setup. So as I said, 18 years of data. They train on 6 years of data. They do this in a rolling way. So for the first prediction, they use the first 6 years and then predict the next year. For the following year, they use the following, they move it by a year and so on and so forth. So it's really, it's a really smart way of doing this. And the 6 years, they actually subdivide into 5 being a training sample and 1 year being validation, which they use for early stopping. All right, they actually had to help OLS and logistic regression because apparently it wasn't a fair fight. So they reduced the number of variables quite significantly by just carrying out some very simple tests regarding the explanatory power of the variables, and they dropped those that did not were not sufficiently significant. And in the end, OLS and logistic regression only had to deal with like 3 to 7 variables out of the 60. Right, so apparently then it was more of a fair fight between the different approaches. And then the question is, okay, so let's say we have this whole setup, right? Oh, sorry, I'm still in the way. We have this whole setup. And now, how do we actually trade this, right? So we have all these predictions. Some of them, I don't know, supposedly are going to earn 20% or something like that. How do we actually deal with this? And the answer is, well, you can just go long the top ones and short the bottom ones. So for instance, the best 25 predictions are the ones that you will hold long, so bet on them going up. And you will short, meaning betting on them going down on the worst 25% of predictions. That way, if the whole market crashes, you have some long positions, you have some short positions, and it shouldn't be that bad, in theory. Okay, right, so top 25, bottom 25, it can be top 10%, bottom 10%, doesn't really matter. They tried many different approaches, and the results were super consistent. So here are the observations. First of all, well, as I've already kind of given away, the neural networks actually managed to outperform the best linear regression and logistic regression alternatives. So really, even taking the worst neural network results, they're still way better than the very best linear regression and logistic regression results. So yeah, even though they tried to level the playing field, still lost. So in case of the classification, they also compared the accuracy in the predictions for the different categories that they created. The accuracy of the neural networks were way higher than that of logistic regression, and obviously that also translated into higher profitability of the corresponding strategies. What else? Oh, right. So classification models, they also compared those to the regression ones that I mentioned earlier on. Classification models outperformed the regression approach, not by as much as they outperformed the other ones, but still. And then they also tried a further variation where they tried different classes. So they didn't just try to predict up or down, but best, second, third, and the very bottom ones. And that apparently did even better. And so here are all the findings in the paper in one plot. So these are basically three tables in one plot, and it displays very poorly. I'm sorry about that. So in green, you can see the neural network. It's this one here. And here are the other ones. It doesn't really matter. The orange one is logistic regression, and the blue one, the one that really sucks, is the OLS one. And so you can see that the neural network in this paper really, really outperforms with, compared to the other ones. And this one, by the way, is not even the best case scenario. All right, so just a little reminder, this is a paper from 2003. So it was a very simple neural network, by the way. And there have been so many improvements. But I decided to show a paper from 2003 just to show you that all of this, you can already outperform just using something very, very simple. Simple neural network. Right, so conclusions. You've seen that neural nets and AI in general are already being adopted both on the sell side and on the buy side, so they're really popular now. On the sell side, I've shown you a couple of examples. So they're really focused on improving the current processes or speeding them up. And we on the buy side are more interested in new data sets, so getting new sources of alpha performance, and getting new insights. And then also combining all the different sources that we managed to find. And neural networks and AI in general, of course, offer many, many new opportunities. They're really exciting also in finance, not just for ABBA and more in the medical field. And the exciting thing is, for us, this is really just the beginning. So we're barely scratching the surface here. And yeah, it's super exciting, as you might hear from my voice. It's a super exciting time to be in this field. Which you may not have heard from many people in finance, but if you're in this specific field, it's actually super exciting. Okay, yeah, that's it. So, questions? I think I rushed through that, by the way. Yeah? You want the mic, or? Yeah.
Can you also tell us a bit about what you do, your job? Not only a paper, but really what can you tell?
Yeah, I have to be super careful about that. Yeah, so basically I rearrange pixels on the screen. No, so the examples that I've picked here are to a degree representative of what we do. I can't go into the specific strategies, nor the very specific methods that we use. So neural networks in general are really, really big, and it's a big part of what we do. It's not just AI and neural networks, by the way. It's machine learning in general. So there are many other methods that are being used. And what can I say? Well, see, the problem is if I'm too specific, then basically others start implementing it, and it stops working because everybody's doing it. Which, by the way, brings me to a slightly related point. There's still discussion whether machine learning works in finance. And I always find it absolutely hilarious because the longer people discuss this, the longer it takes for them to catch on. But I'm completely off topic now. Sorry.
When a client comes to your fund saying, I want to invest the money, what do you tell them to convince them to invest?
Our sales pitch. Exactly. I suck at sales, so I couldn't tell you. So basically what we say is we have a product that we have very high confidence in that captures many different phenomena and is therefore very diversified. So we capture phenomena on different time scales. We capture phenomena for very different markets. So, in all different asset classes. So we have, equities, FX, fixed income, commodities, and volatility strategies. So when one of them is really hot, we're already there. What else do we say? So the good thing about machine learning is it catches on to patterns that you don't necessarily knew that were there. So we have one strategy, for instance, that, no, I can't say that. So essentially, you can spot patterns and see things before they emerge. That is the huge advantage. Yeah, sorry, can't be. I want to say more, but yeah, I'm going to shoot myself in the foot if I do. Yeah.
How much is your best performing product per year? What are the returns on your best?
Yeah, good question. What are the returns? So the thing is, so for regulatory reasons, I cannot really say too much because otherwise I'm running into problems with sales and all of that. But the way we think about it is not so much returns. We think about risk-adjusted returns. So if you think of the S&P, for instance, a lot of people say, ooh, it's been a really good investment. Like since 2009, it's up almost 300% or so. Yeah, except there was a drop of 50%, and so most people would never have had the stomach to really stay in the market. So for instance, in our case, I think our worst drawdown was like 4% or 5% or so. So then a lot of people still feel, yeah, okay, 5%, I can live with this. So if you were to leverage up incredibly, oh, I have to be careful now. Yeah, anyway, if you were to take a risk like a similar drawdown basically, then it would be outperforming because there's this. Warren Buffett said something like the hedge fund industry is lagging behind the S&P or something like that. Yes, but we haven't had a drawdown of 50%. So it's a shitty comparison. Sorry? If you look at the Sharpe ratio, so the risk-adjusted returns, yes, by far. So the S&P has a Sharpe ratio of like 0.6 or so, which is terrible. And so hedge funds, it depends on what kind of strategy that you look at. So very, very simple stuff will get you to like 0.8 or 1. With equities, you can get to 2, 3. With high-frequency trading, you can get well above 5. So I would say that beats the S&P, hands down. Yeah?
I don't know if you guys do high-frequency trading.
No, we do not do HFT.
Do you have this flash crash issue? Or
No.
would you ever unplug your algorithm when returns are not below some threshold?
Right. So the question is whether we would actually stop our algos if the performance was really abysmal. So usually, we have a process for that. So we basically have portfolio reviews quite frequently, and we analyze why things are going wrong when they're going wrong. There's always something that you cannot foresee. For instance, there's very few people who thought that a president of the United States would threaten with nuclear war via Twitter 5 years ago. And so those things you cannot foresee. And so you make some losses, for instance, on the S&P or whatever, and you know why it happened. And then you might say, okay, current administration is not that stable, so you reduce exposure. I'm sorry, it's a very stupid example, but it's a very simple one, right? So we constantly review our algos, their performance, and whether they're performing as we would expect, and whether they keep capturing the effects that we think that they are capturing, which is a bit tougher to do with ML, but we still know what to compare them to. So I hope that answers your question, more or less. Okay. Any other question? Yeah.
I know nothing about finance, but do you analyze every sector then specifically? So you have different algorithms for each and every sector. So if there would come something new on the market, you wouldn't capture that. So let's say you have all your algorithms, maybe, yeah, you do all of them, but then something new comes up and drives up the whole stock market would go up, but you would not be a part of that because it's outside of your...
Right. So the question is whether we train stuff sector specifically or we do it more generally. And then I think there was a second question regarding new phenomena, that whether we managed to capture those. Yeah. So we have some algorithms that are sector specific, so specific to commodities, for instance, so asset class specific. And we have others that are more general. So it depends on what you think you're capturing with it. So I gave the example of trend following, which is just based on human behavior, that we like to, we see something go up and we fear missing out, or the information is, anyway. Those are generally valid. Now, regarding new phenomena, so we have some algorithms that are retrained quite frequently. So they will catch on. If it's an entirely new phenomenon, it might not have the necessary amount of observations for it to actually have an impact. And there's two things, right? You want to catch on to new phenomena, and you don't want to forget about old ones. So in machine learning, it's referred to as catastrophic forgetting. And so we actually, in our data sets, we enrich them with past observations as well, so that neither new ones have an unnecessary high weight, nor that it forgets about what happened, for instance, in 2007-8. But if there's something like brand new happening and it's never seen before, it really depends on whether it falls into any of those categories that we already tried to capture, which we might, by, I don't want to say by accident, but by capturing something similar. If it's something never before seen, then I can't give you an answer because I don't know what it would be.
Yeah. Would you also get like a specific name of a thing to buy? Or is it more that you get that the oil industry is going well, but do you get like specific names?
Yeah, so the question is, what is the actual prediction? So this very much depends on what it's for. So for instance, in equities, you get prediction regarding the performance of certain stocks. So it basically tells you buy XYZ, short ZYX. For commodities and so on, it tells you what kind of position you want to hold. So do you want to be long oil? Do you want to be short oil? That kind of thing. By the way, I'm not recommending any of those positions. I don't even know if XYZ and ZYX exist. But anyway. Yeah?
So you wrote a paper about overfitting?
Yeah.
Right?
Yeah, I wrote, yeah.
Tell something about that in general?
Yeah, so at AHL, we had one of those academic sessions. They're not called that, but I forgot the exact name, with a couple of professors and our very senior people and myself, because I had to write it down and also make a contribution. Okay, I should phrase that more favorably. Anyway, so we discussed overfitting and basically its impact on the investor. And essentially the thing is that quants, whether we like it or not, and pretty much anybody in data science, we overfit to some degree. Because we test a whole bunch of things, and some work, some don't. And some people are more careful about tracking all the things that we've tried. For instance, I always write it down. And so research reports in the end have this list of, I tried this, this failed, this sucked really bad, and so on. So keeping track of what you're doing is crucial, because you can have a strategy that seems to perform amazingly well because you completely overfit it, and you actually put it into live trading in the worst case, and it kind of does the opposite, right? So in this field, it's absolutely crucial to be aware of overfitting. Did that answer the question in any way? A little bit. Okay, what did I miss?
When you talk about neural networks and you talked about linear regression,
Mm-hmm.
I mean, I know linear regression, and it's easier to interpret, it's easier to, you don't have as many parameters,
Yeah.
but you can go after it and explain it. And I
Right,
think,
yeah.
in neural networks, it's really hard to explain how do you.
Yes, so basically, yeah. So the question is basically how one can justify the additional number of parameters, right? Because you have a very simple to interpret model with linear regression, and you have something that is highly complex in the case of a neural network. Well, yes. So what we do and what should be done in general is you always have a benchmark model. So you have something to compare it to. And if with more parameters you get the same results, then you take the least complicated model, which would be linear regression. in this case, these guys showed very clearly that the additional parameters were justified. I mean, it outperformed really, really, I mean, this is quite cool. And when you calculate Sharpe ratios for these guys, it's also very clear that they outperform. And so in this case, I would say it's justified. In other cases where you see like a minute change, no, not justified. Unless, of course, you cannot, like, for instance, satellite imagery one. Those I really like because it's very difficult to process those kinds of images without neural nets, right? So but if you have a task where linear regression is an option, then you need to keep that as a benchmark. And yeah.
Can I maybe say?
Yeah.
Maybe I can say a few words on how we deal with it at Eva. So we of course do everything you should do with cross-validation, and then we have a separate validation set that we use only at the very end. But since the stakes are so high, we have now split the validation part of our algorithm. So we are not the final validator of our own algorithms. We have our clinical team who are collecting data that we have never seen. And before we are allowed to, just before releasing or just going for the go, they will validate it on their data that